Yeah, today we will do 6.6 and 6.8, but before I go on, let's do some extra problems from 6.4. It's more about reviewing what you have learned in Calculus 1 and put things together with what we have with uh, 6.1 to 6.4. So number 85, find the volume of the solid obtained by rotating the region under the curve y equals to 1 over square root of x plus 1. I think it's approximately like this. It's approximately like that. From 0 to 1. It doesn't matter. It doesn't have to be straight. Okay, it doesn't have to be straight. Let's say it's like that. Okay, and this is the y equals to 1 over square root of x plus 1. Now, if we take a slice of this curve here, okay, and rotate that, you will see that the radius of this disk is basically the y, right? So the volume will be the integral from 0 to 1 of the volume of each disk, which is pi y squared dx. That's the volume. But because the volume of each disk is volume for each disk is pi y squared dx, right? Where the y is the radius, dx is the thickness of that disk. Okay, now then the volume of this solid, therefore, will be the summation of those little disks, very thin disk. Oh, that's the setup. Of course, then we can take the pi out, integral from 0 to 1 of 1 over x plus 1 dx, right? And this will be, you can do substitution if you like, okay, but you will get this is pi natural log of 2 minus natural log of 1. But natural log of 1 is 0. This is pi natural log of 2. What happens if instead we have the curve being rotated about y-axis? 1 over x squared plus 1. 1 over x squared plus 1 looks like this, I think. Okay, but from 0 to 3, now we will rotate that with respect to the y-axis instead. So if I take one, what do you call it? One strip from there, whose thickness is dx and height is y, and rotate this way, I get the shell, right? I get the shell. Now, what's the volume of that shell? Volume of that shell will be the circumference 2 pi x times the height, which is y, times the thickness of that shell, dx. Now then, the volume of the resulting solid will then be the total volume of such shell from 0 to 3 of 2 pi x 1 over x squared plus 1 dx. Let me take the pi out. And I will do substitution here. Let u equals to x squared plus 1. So my du will be 2x dx. Okay, so 2x dx is my du. My u is x squared plus 1. Now how about u3? When x equals to 3, then u3 is 10. When u equals to 0, when x equals to 0, then the u is 1. That's what happened to the limit of integration. So this is pi times integral from 1 to 10 of 1 over u du. That's pi ln u from 1 to 10. That's pi ln 10 minus ln 1, but ln 1 is 0 then, so that's pi ln 10. It's about the setup though. It's about the setup. I have to say that when I ask this kind of question in number 85, 86, if students don't know how to do this, it's usually because they don't know how to set it up. But once they are able to set it up, they can integrate that easily. Okay, so in other words, sometimes what makes you not able to move forward in Calculus 2 is not because you don't understand Calculus 2, but your foundation in Calculus 1. That's for number 86. Set up the integral and then compute. Number 93. Use definition of limit. Use definition of derivative. Use the definition of derivative. To prove that limit x going to 0 of natural log 1 plus x over x is equal to 1. I somehow think I went over this in my lecture when I went over 6.4. I really think I did that, but just in case I forgot, let me go over this. The technique of finding derivative here is actually a quite common technique, especially at the basic level. We will do it this way. Let fx equals to ln of 1 plus x. Now notice that f0 equals to ln 1, which is 0. So limit x approaching 0 of ln of 1 plus x over x, this is actually equals to limit x approaching 0 of fx minus f0 over x. Is it right? But by definition, this is actually the derivative of fx at 0. Is that right? Now the derivative of fx at 0 will be f prime x equals to 1 over 1 plus x, which is 1 over 1 plus 0. That's equals to 1. So we are done. Okay, that's for number 93. Number 94. I think number 94 is the one I did usually. Show that limit n goes to infinity of 1 plus x over n to the n is equal to e to the x for x positive. Proof. Let y equals to 1 plus x over n to the n. Now, the idea is I will apply natural log first, and then from there I will apply the limit. Okay, so natural log of y equals to natural log of 1 plus x over n to the n. On the right hand side is n times natural log of 1 plus x over n. That's what our natural log of y is. Now notice that I can apply limit on the left hand side. Limit n goes to infinity of natural log of y equals to limit n goes to infinity of n times natural log of 1 plus x over n, which I will rewrite on the right hand side as natural log of 1 plus x over n over 1 over n.
I have a question, Thomas.
Uh-huh.
So why at the fourth step did you why are we able to use limit as n goes to infinity?
Well, because we are actually chasing this.
Right.
That's what we want.
So why would you put it why that step? Why do we know at that step that we're able to do that? Could we have not used it before?
That's basically the consequence of what we have before. If ln y equals to that, then the limit must be limit both sides.
Oh,
Right? I apply limit on both sides.
okay. So I mean, that's all you're doing is you're adding the limit because we want to get there. You just chose to do it after that step because it.
Yeah, because well, basically the previous step applies for every n, right?
Mhm.
So it must apply when n goes to infinity,
Okay, I got you.
right?
Thank you.
Now then, what happened now? We have this is equal to. Oh, you know what? Let's see the left hand side first. The left hand side. This is limit of natural log is equals to natural log of limit. Limit of a function is equals to the function of limit if it is continuous. Now, the thing is what happened on the right-hand side. The thing is what happened to the right-hand side. Now, we know if n goes to infinity, then 1 over n will go to 0 positive.
Hey, Thomas.
Hey.
Why did you put the n? Why did you put it in the denominator 1 over n?
Well, because n on the numerator is equals to 1 over n.
Oh, okay. So you just changed it. You just brought it down. But what is the reason?
The reason is because I want to play further from there. If n goes to infinity, means 1 over n goes to 0 positive.
Did we learn this in calculus?
Calculus 1, supposedly.
Oh, okay.
Yeah, if n goes to positive infinity, something very, very big number, right? Very big positive number, then the reciprocal must be very close to 0, but still positive.
Okay.
Right? Okay. Now then on the right hand side here, I will do substitution. If n goes to infinity, then 1 over n approaching 0 positive. Now I can call this, let's say, h now. H is the reciprocal of n. Okay, so I will do that substitution. Limit h going to 0 positive of natural log of 1 plus xh over h. Notice my substitution.
Yeah, so basically you get the xh because x over n is equivalent to x times 1 over n.
That's right. That's right. That's right.
And that's how you get the h at the bottom.
Now then, from here, you will see, actually there's something I didn't do earlier that I supposed to do. You will see this is equal to x, but I don't really know how to explain it here for now. Let me do it this way. Oh, not yet, not too fast. Now, if x going to 0, h going to 0, then xh, which I will call u, will also go to 0 positive. Imagine if I multiply by the h, which is very close to 0, by x, and I call that u. Limit 1 plus xh over, now this is xh over x. Will that be okay? So I basically replace the h here by xh over x.
Why is it over x? Sorry.
Well, x times h over x is h.
Oh, okay.
Yeah, so I just do manipulation here. Now then, let me do extra one step. This is like a little step that if you know the idea, you will have skipped this step. This is getting pretty complicated to prove. It is true. This is number 94, the last question of that section. Do I expect this type of substitution for us? I want you to eventually get it, but we will not get at all if you never really see it, right? Okay, so I think this way of manipulating the limit notation, is something I show you a couple of times already. Okay, now is this the only way to do it? No, this is not the only way. This is one of many ways, right? Okay, this is one of many ways to prove this equation. But in every proofs that you do, all of them you will see involve this kind of substitution. Okay. Okay, now let me go back here. I will rewrite this first. So basically the x that I have here, that's the denominator of denominator, right? Okay, maybe I write it this way then. Maybe I write it this way. This is the same to multiply by x over xh. Is it right? Now, I will put this again together under the same fraction. Okay, but at the same time, I will do substitution. Call that u, limit u going to 0 positive of ln 1 plus u over u times x. But according to what we learned in number 93, this expression here is equal to 1.
Damn.
Take a look. Take a look. That's what we have from number 93. Limit blah approaching 0 of natural log of 1 plus blah over blah is 1. Okay, so then because when we look back, okay, we look back. So we already have natural log of limit n goes to infinity of y equals to x, then changing it back to exponential form, limit n goes to infinity of y is e to the x. Therefore, limit n goes to infinity of 1 plus x over n to the power of n is equal to e to the x. Now, the thing is, this expression here is one very important equation in math. It's one very important equation in math. Okay, this is one way that we define the number e, natural number e, in other textbook. So e is an irrational number that is defined in many different ways and still get the same e. That's the thing. That's how natural this number is. Do I need to memorize the proof, Thomas? Don't try to memorize it, but try to think about how the idea. Because what we did here is actually limit of exponential, logarithmic limit. Logarithmic limit. So instead of attacking the limit right away, we take a look on the logarithmic first, the log of that expression, take the limit, and then you change it back to exponential. So you see, so you start from y, you apply natural log, oops, you apply natural log, and then you apply the limit. Now then, the thing is, if the function is continuous, then you can switch the limit and the natural log. What am I doing? Natural log of limit. Then you get the limit of y. Okay. So instead of attacking from y going to limit right away, you go around that way. Now, somewhere in between, you need to pay attention to the notation of limit. Here's the thing though, I also noticed that a lot of students, very likely you included, when you come to calculus 2, in your calculus 1, your teacher didn't emphasize the need of writing this notation. Some teacher, not all, but some. Some of them say, oh, you don't need to write it until very end. But that's not appropriate. That's not the right way to teach. Okay. Just like me, when I educate my son, when he asks something from us, from anybody, especially from someone more older than him, he needs to first use the word please. So the word please has to come first, not after. Not like, do this for me, please. No, 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 no. It's supposed to be, please do this for me. Do this for me, do this for me. I want it this way, please. It's like your please comes at the end. No, you should say please first. That's why I say to my son. Of course, my wife thinks it's not a big deal. I said, well, for me, it's a big deal. They need to, this kid needs to first know that he's begging for something, asking for help. So the word please should come first. Okay, now we will encounter this equation again in future. There's somewhere in, I think 6.8, yes, somewhere in 6.8. But if you actually know this thing, it will be a lot easier for us to attack this problem later on in 6.8. Basically, we create one more way to compute other things. 6.6. Now, in this section, you need to memorize 3 basic integration. The inverse trig function, you know what? Let's review the inverse trig function first. Keys. For sine y equals to sine x to be 1-to-1, the domain is restricted to, the domain is restricted to negative pi over 2 to pi over 2, which I usually say quadrant 1 or quadrant -1. Basically, on the quadrant system, it will be here and here. Therefore, so when we say sine inverse of something, the result will be between negative pi over 2 to pi over 2. Okay, of course, for x from 0 to 1. Negative 1 to 1. That's for the sine. For tangent, to be 1-to-1, the domain is restricted to negative pi over 2 to pi over 2. Now, I don't think you memorized this yet. Okay, I mean, you should have memorized that in trigonometry class. But You still remember that again here. Okay, basically, this is what happened. For sine function, the graph of sine function looks like this. Right? And it goes indefinitely far. This is definitely not one-to-one. Now then, for us to make it one-to-one, we restrict the domain from negative pi over 2 up to pi over 2. So this is the window. That's for sine. How about tangent? The graph for tangent, again, because it's a trigonometric function, so it is not one-to-one. However, to restrict that to one-to-one situation, then we use from negative pi over 2 to pi over 2, not including the endpoints, because the endpoints right at negative pi over 2 is an asymptote. Right at pi over 2 is also asymptote. That's why we don't include the endpoints here. Okay, now, but consequently, so tangent inverse of x will be from negative pi over 2 to pi over 2. Okay. Lastly, for y equals to secant x to be one-to-one, the domain is restricted to let's say first, what does the graph of secant x look like? The graph of secant x looks like this. With asymptote at pi over 2 and 3 pi over 2. Now, by convention, they choose the domain to be here, quadrant 1 and quadrant 3, to make it one-to-one. From quadrant 1 to quadrant 3. So it's restricted to from 0 to pi over 2, not including pi over 2 because it's undefined there. Then union from pi to 3 pi over 2. Now the thing is, this restriction turns out to be not uniform. In other words, different textbooks restrict that differently. Okay, for sine and tangent, for sine and tangent and cosine, the restriction actually clear. But for cosecant, secant, cosecant, the restriction is not clear. Different textbooks define it differently. So our textbook define it this way. But the purpose is later on for derivative. Okay, now with this said, let's answer some questions first, just to warm up our mind about inverse trig function. For example, if we look at the exercise set, between number 1 to number 10, is there any problem you want me to do? From number 1 to number 6. Maybe I do even number first, number 2, 8. What is tangent inverse of radical 3? So the way we think is tangent what equals to radical 3. Okay, and that angle has to be between negative pi over 2 to pi over 2 to keep one-to-oneness. What is the angle? Because the argument is positive, then the angle must be quadrant 1. Now, tangent what in quadrant 1 gives us radical 3. That will be, uh-oh, you don't remember? Pi over 3. Okay? Oh, please remember that though. Please remember that 0 degree, 30 degree, which is pi over 6, 45 degrees, which is pi over 4, 60 degrees, which is pi over 3, 90 degrees, which is pi over 2. The sine for 0 is 0, 1/2, radical 2 over 2, radical 3 over 2, 1. Cosine theta, this is 1, radical 3 over 2, radical 2 over 2, 1/2, 0. For tangent 0 is 0, tangent 30 degree is 1 over radical 3, tangent 45 degree is 1, tangent 6 degree is radical 3, and tangent 90 degree is undefined. You need to memorize this, at least this. Not to say the cofunction, I mean the reciprocal, secant, cosecant, cotangent. How about number 2b? What is secant inverse of 2? Secant inverse of 2. Let's call this theta. Let's call this theta. So 2 equals to secant theta. But if secant theta is 2, then cosine theta will be 1/2. Now the thing is, cosine is restricted to quadrant 1 and quadrant 2.
Is it pi over 3?
That's pi over 3, that's right. So theta equals to pi over 3. Okay. If you can jump directly from here to here, that would be great. Okay, if you can jump right away, it would be great, preferable. Now, usually when I go over this kind of thing, and then the student suddenly come in, that person will say, "Oh, Thomas, this is too easy. I know this already. I know you know it already. You're supposed to know this already. So what's the reason you do this? Because very likely you don't remember it." That's why I go over that again. Okay. I mean, it's been quite a while. At least you have at least 6 months in between pre-calculus, the last time you see this, and calculus 2. So expecting you to memorize this special number, it's actually not too much, but I do not want to be unreasonable. Okay, so let me assume you don't remember that, but you have to recall it really fast. Okay, now, let's call this theta. Therefore, negative radical 3 equals to cotangent theta. Therefore, tangent theta will be negative 1 over radical 3. Now, the thing is, the restriction for tangent is quadrant from negative pi over 2 to pi over 2. So what will our theta be? It will be negative 30 degrees, pi over 6. Okay, again, if you can do it, jump right away, go for it. How about number 4b? Number 4b, how about arc sine of 1? Arc sine of 1. Basically, sine inverse of 1. That's pi over 2, right? Yeah, sine what equals to 1? That's number 4b. Number 6a. Number 6a. What is tangent inverse of tangent 3 pi over 4? Tangent in quadrant 2 is negative. 3 pi over 4, that's negative 1. Now, tangent inverse of negative 1, however, is negative pi over 4. Tangent what angle equals to negative 1, and that angle is in negative pi over 2 to pi over 2 interval. On the other hand, there's the nice thing about tangent inverse and sine inverse, not for cosine inverse. For tangent inverse and sine inverse is that you can also do the following. Tangent inverse and sine inverse are odd functions. So tangent inverse of negative 1 is negative tangent inverse of 1. But tangent inverse of 1 is pi over 4. Okay. That's only for tangent and sine. Part B is number 6b. What is cosine of arc sine of 1/2? Arc sine of 1/2 is 30 degrees, pi over 6, and cosine pi over 6 is radical 3 over 2. That's Mickey Mouse. Now, but I would like to go on with the second method of doing number 6b, which is actually more important. The second method, method 2. The second method of doing this, we let theta equals to arc sine of 1/2. Therefore, sine theta equals to 1/2. I am anticipating what if we replace that 1/2 by x instead. Then what will happen to the sine of arc sine of x? And the way we do it will be as the following. The sine theta equals to 1/2. Therefore, I can draw the triangle, the right triangle. Let's say this is theta. This is 1 over 2, right? Opposite over adjacent cosine. By Pythagorean theorem, and this is radical 3. Okay, then what is cosine theta according to that picture? That's radical 3 over 2, right? But we already answered the question because the question is, what is cosine of arc sine 1/2, which is theta. Okay, now using this method number 2, let's see question number 12. Simplify tangent of sine inverse of x. The work, you will say, let theta equals to sine inverse of x. And then you write, oh, then sine theta equals to x, which is x over 1, right? You draw the triangle. If this is theta and this is right angle, sine theta is x, which is x over 1. This is x, this is 1. Then by Pythagorean theorem, this is 1 minus x squared. Now, the tangent of this theta is x over square root of 1 minus x squared. Therefore, we finish answering that main question. Tangent of sine inverse of x is x over square root of 1 minus x squared. Now, from here, a little bit more before we get into the derivative and integral. A little bit more. It's still review from trigonometry. Number 10, for example. Number 10. Compute cosine of tangent inverse 2 plus tangent inverse 3. I asked this question in my trigonometry class before. Maybe not yours, Doglins. Okay, but I did ask this kind of question in my trigonometry class.
It looks familiar.
Yeah, well, because you see it here, and your calculus 2 teacher may just assume that you have seen that before. But the trick is basically assuming let A be tangent inverse 2 and B be tangent inverse 3. Our goal is to draw these two triangles that give us this value. So if this is A, this will be 2 over 1. So by Pythagorean theorem, this is radical 5. While for angle B, if this is angle B, tangent B is 3, gives us 3 over 1. By Pythagorean theorem, this is radical 10. Now the thing is, if we go back, that cosine of tangent inverse 2 plus tangent inverse 3 is equal to cosine of A plus B, right? Now then, at this point, I hope you can rememorize the formula for sum and difference of trig functions. So cosine of sum is cosine A times cosine B minus sine A times sine B. Thomas, our test is open notes, right? So I can just look at the notes. Yes, you can, but at the same time, if you don't memorize that, it means you don't internalize that. If you don't internalize that, you won't be able to realize this is what you need to do. So if I were you, I memorize it. Okay? If I were you, I would memorize it. Don't worry, you have at least 3 weeks to memorize that. Now, then from here, I look back. What is cosine A? Cosine A, according to the pictures on the left-hand side, it's 1 over radical 5. Cosine B is 1 over radical 10. Minus sine A is 2 over radical 5. Sine B is 3 over radical 10. How do you recommend memorize things like this? If you have memorized that before, then reading it, maybe write it on a cheat sheet and bring it everywhere with you. The way I usually do it is this though. If I already memorized it before, right? I write it on cheat sheet, but I write it many times. So with the formula sheet, the same formula sheets, right? I may have like 4 or 5 copies of that, and then I stick it everywhere. One of them, 2 of the places that I always stick my formulas for me to memorize are next to my bed and in my restroom. Okay, staying at home, it's going on my walls. The thing is, which wall? The best one is right in front of you when you do number 2. Okay, because unless you always bring your phone with you, right, then you may want to stick in front of your phone. Right, so that before you use your phone, you see the trig function first. Trig formulas that you need to memorize first. Well, anyway, let me go on. And this will be 1 minus 6 over square root of 50. But square root of 50 is 25 times 2, right? So that's 5 square root of 2. That's negative 1/2. Yeah, in the past, I have this follow-up question in my trigonometry class or my pre-calculus class follow-up. Which quadrant
Professor, wouldn't the answer be radical 2 over 2?
Yes, thank you. I forgot to write it. Which quadrant is this tangent inverse 2 plus tangent inverse 3 located? Which quadrant is it located? First argument, cosine of this expression is negative. So from there, we know this angle is in the quadrant where cosine is negative. Is in either quadrant 2 or quadrant 3. Right? Cosine is negative is in quadrant 2 or quadrant 3. Second, we know that tangent inverse 2 must be in quadrant 1. Yeah, tangent inverse of positive number must be in quadrant 1. Okay, tangent inverse 3 also in quadrant 1. Now that implies A is between 0 to pi over 2. B also from 0 to pi over 2. The sum must be between 0 to pi. In other words, A plus B must be in quadrant 1 or quadrant 2. Now, together, step 1 and step 2, what can you say about this angle? Which quadrant should this be? From the first point of view, is between quadrant 2 and 3. From another point of view, must be quadrant 1 or 2. So this must be in quadrant 2. Okay, so there's actually so many things we get here. Okay, so yes, you need to memorize that though. Memorize this sum and difference formulas and double angle formulas. And then power reduction. Half angle formula. Memorize these formulas. There are two more groups, but this first. In the next 2 days, you need to memorize this first. Let me see if your textbook has that. It's in this one here. Stop sharing. Let me show you the video. Okay. If this is your textbook, and this is the back of the front cover, then you will see that here. Okay, the back of the second cover, the inside cover. Okay, the paper is kind of like manila paper instead of the regular paper. Okay, but the second column of the inside of the second cover. Okay, it's there. Now, if I were you, don't just read from there though. If I were you, I would just copy. I will copy from there, copy that into some cheat sheet, write it down many times. Okay, and then hopefully by writing it down many times, you can memorize that. Okay. I always have in mind from what my middle school teacher told us though, that you learn math, including memorizing the formula, from writing, not from reading. So you can say that I read it, I understand it. Yes, it's one thing about understanding it. It's another thing to reproduce that yourself. Okay, that's why when I do things in class, you may understand because I'm the one doing the thinking. You do the copying only, right? It's different from if you are the one doing it, and then I'm the one grading it. You know. Okay, so please memorize this. There are more formulas, but the others are not that important, at least not for now. That's product to sum formulas, and then sum to product formula. You definitely need this before we get to chapter 7, which is, I think, on Wednesday. Yeah, on Wednesday we will have at least starting 7.1. Okay, now once we get that, then we will have this in our cheat sheet. Have this in our cheat sheet. If the derivative of sine x dx is 1 over square root of 1 minus x squared. The one on the right hand side, I don't memorize, but I think now I already memorized it, but you don't need to. This is negative 1 over square root of 1 minus x squared. Derivative of tangent inverse, I'm sorry, this is inverse. Tangent inverse x is, respect to x, is 1 over 1 plus x squared. And the derivative of cotangent x respect to x is negative 1 over 1 plus x squared. And the derivative of secant inverse x respect to x is 1 over x square root of x squared minus 1. The derivative of cosecant x respect to x is inverse. I keep on forgetting the inverse. This is negative of 1 over x square root of x squared minus 1. I believe I show you the proofs for the first column in my lecture. So please memorize. The one you need to memorize is this one. This is the one you need to memorize. Over some time, after doing some problems, then you will memorize the second column eventually. Okay, but the key is actually in the following point of view. The key is as the following. We know that sine inverse x plus cosine inverse x is equal to 1. I'm sorry, equals to pi over 2. If you can prove that, then so this is the first thing we need to prove, okay? And I will show you later on. Then once the first one is true, then the second one is basically implicit derivative. If you do implicit differentiation, then the derivative of sine inverse x respect to x plus the derivative of cosine inverse x respect to x is equal to the derivative of a constant respect to x, which should be 0. Now, we don't know this part, right? That's the one in question. But we already know that the derivative of sine inverse respect to x is 1 over square root of 1 minus x squared. Therefore, the derivative of cosine inverse x respect to x must be negative 1 over square root of 1 minus x squared. The thing is, how do we prove this? How to prove sine inverse x plus cosine inverse x equals to pi over 2. There are two ways to do this, but the first way based on a right triangle, let's call this part A. Suppose you have a right triangle, okay, whose theta, sine theta is x over 1. Now, cosine inverse of x over 1 will be this angle here. Let's call this angle gamma. Now, you see that theta plus gamma always pi over 2. So let theta equals to sine inverse x. So sine theta equals to x. Now the complement of that theta, which is gamma, is have cosine the same value, right? But we know this theta and gamma are complementary, therefore the sum must be pi over 2. But I don't like this proof because it doesn't have, it doesn't anticipate what if the theta is more than 90 degrees or if theta is negative angle. So the other way to do this, the harder way, but more comprehensive, anticipating what if the x is negative number, let's say. Okay, what if the x is negative number? So we apply the following. Let theta equals to sine inverse x and gamma equals to cosine inverse x. Sine theta equals to x, cosine theta equals to x. And we draw the triangle. If this is theta, this is x, this is 1. If this is gamma, as if this theta and gamma has no relationship at all. Now then we look at, for example, the sine. What is sine of theta plus gamma? It's sine theta cosine theta plus cosine theta. I'm sorry, sine theta cosine gamma plus cosine theta sine gamma. Sine theta is x over 1. Cosine theta is also x over 1. Cosine theta is square root of 1 minus x squared. Sine theta is 1 minus x squared. So I get x squared plus 1 minus x squared equals to 1, whatever the x. On the left hand side, I have sine of sine inverse x plus cosine inverse x. Now, the reason I use sine, you can also use cosine if you want, right? It's because sine angle equals to 1 only happen at one angle, that is at pi over 2. Sine blah equals to 1 implies that blah must be pi over 2. Okay, that's the proof. This is a more comprehensive proof. This is a more comprehensive proof. Part A is visualization, but the thing is it doesn't anticipate what happens if x actually is a negative number. Let's say if x is 1/2. If x is 1/2, then you cannot even draw the triangle anymore, right? The right triangle. But once you memorize these formulas, these 3 formulas here, then we are actually ready to go with the derivative and the integral. Okay, now let's go on with the derivative part. Take a look, for example, between number 22 to number 35. 22 to 35, pick 3 questions. (22 to 35). Nobody said anything.
Can you do number 33?
Number 33 is one of them. Any else? No more. Let me do number 33 first then. Number 33, we have ht. H as a function of t is equal to cotangent inverse of t plus cotangent inverse of 1 over t. Now then, the derivative of cotangent is the opposite of the derivative of tangent. Okay, so this is negative 1 over 1 plus t squared plus negative, or let me change that to negative by the way, minus 1 over 1 plus 1 over t being squared times the derivative of 1 over t, the chain rule. It's negative 1 over 1 plus t squared minus this is 1 over 1 plus 1 over t squared times negative 1 over t squared. Oh, you know what? I can just, the negative with negative cancels. So hold on. Cancel to the next number, I guess.
Thomas,
Yes.
why is only one of them a chain rule?
Because this is already t, no need for chain rule. Yeah, we do the derivative with respect to t. It's already t there.
Oh,
You can do the chain. Okay, what is the derivative of t?
we just won.
Yeah, okay. Yeah,
Okay, got it. All right.
And then the negative with negative becomes plus here. On the top, 1 times 1 is 1. At the bottom, t squared times that expression is t squared plus 1. But they are actually the opposite term, so the sum is 0. I mean, the derivative is 0. Now, this actually implies something, though. If the derivative of a function is 0, what can you say about that function? If the derivative of a function is 0, then that function must be constant. Right? It must be constant. Now, we don't know what is that constant, but at least we know it must be a constant. You can plug in t equals to 1. Okay, for t equals to 1, then h1 equals to cotangent inverse of 1, which is pi over 4, plus cotangent inverse of 1, which is pi over 4. The sum is pi over 2. So ht, which is cotangent inverse of t plus cotangent inverse of 1 over t is pi over 2. This is just a consequence of what happened if the derivative is 0. The derivative of a function is 0 means that function itself must be constant. That's number 33. Pick 2 more questions from here.
What about 34?
Okay, 34. Number 34, y equals to tangent inverse of x over a plus natural log square root of x minus a over x plus a. So the derivative of tangent inverse is 1 over 1 plus blah square times the derivative of blah plus the derivative of natural log is the reciprocal times the derivative of the blah. Let me make it nicer now. This is 1 over 1 plus x squared over a squared. Derivative of x over a is 1 over a plus square root of x plus a over square root of x minus a times the derivative of that. Ooh, that's ugly. I happen to do it long way already. So this will be x minus a over x plus a under square root. No, I don't. No, it's not. Why not? The denominator only. It's square root of x plus a squared. The numerator, the derivative will be 1 over 2 square root of x minus a times square root of x plus a minus the derivative of the denominator, which is 1 over 2 square root of x plus a times square root of x minus a. That's what I need to simplify. Let's deal with this one first. I will multiply the top and the bottom by a squared. Okay, I will multiply the top and the bottom by a squared. It will give me a squared over a squared plus x squared divided by a, right? 1 over a plus when do I want to simplify that first? Let me simplify this. Let me simplify this. So I will multiply by the LCD. Okay, I will multiply by the LCD. I pick the 1/2 out. I put it at the front. Square root of x plus a over square root of x minus a. So that's what happened here. This guy here is now here. I took the 1/2 out. I factored the 1/2 out. And then I multiply the top and the bottom by square root of x minus a times x plus a. And I will get x plus a minus x minus a over square root of x plus a squared square root of x plus a x minus a. Or do you want me to go slower there? Let me do it below so that you see the detail. Okay, let me do it here. So we will simplify the following: square root of x plus a over square root of x minus a over minus. Let me make sure I copy the question. Minus square root of x minus a over square root of x plus a big over square root of x minus a squared. X plus a squared at the bottom. Yes, that's what it looks like. Now, what I did was I multiplied by the LCD square root of x minus a square root of x plus a. That's why the bottom looks like that. You see the bottom here? That's what I have here. the thing is, when I multiply the first term here by this, notice that x minus a cancels. Only x plus a under square root being squared. And this guy, when I multiply by this, square root of x plus a cancels, I get square root of x minus a being squared. While at the bottom, I have square root of x plus a being squared times square root of x plus a, x minus a. Actually, they simplify a lot further. X plus a minus x minus a. Okay, so you will see on the top that would be 2a. While at the bottom we will have x plus a in parentheses square root of x squared minus a squared. Okay, that's the big work. That's big work. Okay, let's come back here. I need to have some space. So the first term becomes only a on the top. A over a squared plus x squared plus 1/2 square root of x plus a over square root of x minus a times 2a square root of x plus a being squared square root of x plus a, x minus a. Actually, it turns out to be a very nice expression. This is x plus a square root of, it's already under square. Let me do it this way instead. Now you notice that this part here cancels with this. That's a, that's equals to a over a squared plus x squared. The 1/2 and 2 cancel, so I have only a on the top. At the bottom, I actually have this square root of x plus a being squared times square root of x minus a being squared. I wonder if you can tell me what will that be?
Thomas, what did you do with 1 over a?
I cancel with a.
Oh, okay, I see. All right, thank you.
What happened with the denominator? I get x squared minus a squared. Now, you chose number 33 and 34. I don't know if you already tried the previous questions, but you should do that first. Okay. The key is really to memorize. The key is really to memorize this derivative for that. The ones here. The one I circle in, I box in yellow. You have to memorize that first. And then you apply that in practice, including all the chain rule thing. Okay, now let's take a break. 10 minutes break. We come back at 8:55. Then at that time, we continue with maybe with the limit, maybe 1 or 2 questions. And then with the integral. Very likely we won't be able to finish 6.8 today. Very likely. But that's okay. Don't worry. Is there any more question you would like me to do from that derivative part? If not, then I go on with the limit. I go on with the limit ones, the one which is your issue, right? Let's say number 43. I think this one is quite easy. Number 43, limit of x approaching -1 from the positive side of sine inverse x. So take a look on the graph of sine inverse x. The graph of sine x looks like this. That's the graph of sine x. Now sine inverse will be the reflection, the one-to-one part, right? The sine inverse x will be the reflection of that graph with respect to x equals to y line. So the line will look like, the graph will look like this. Now the thing is, you are approaching -1 from the right hand side. What will the value be? -π/2, right? -π/2. And actually, because of the continuity, right? Because of the continuity, now notice that you can just do this right away. This is sine inverse of -1, which is -π/2. Okay, now that's not the case, however, for number 44. Number 44, we have limit x goes to infinity of arcus cosine of 1 plus x squared over 1 plus 2x squared. But limit of function equals to function of limit, as long as it is defined there. So arcus of limit x goes to infinity of 1 plus x squared over 1 plus 2x squared. From what we learned from calculus 1, arcus cosine of that limit is, I will divide the top and the bottom with the highest exponent. So 1 over x squared plus 1 over 1 over x squared plus 2. Then you bring the x goes to infinity, which will give us arcus cosine of 0 plus 1 over 0 plus 2. That's cosine inverse of 1/2. Now, what will that be? Π/3. Number 45. Limit x goes to infinity of arctangent, or let me write it as tangent inverse of e to the x. But when x goes to infinity, what will e to the x go to? goes to infinity also, right? So I can write it this way. This is limit e to the x goes to infinity of tangent inverse of e to the x. That's limit u goes to infinity of tangent inverse of u. Just little substitution there. So what is tangent inverse of infinity? What is the angle such that tangent theta approaching infinity? Pi over 2. Okay, tangent pi over 2 is undefined because from the left hand side it approaches from infinity. Now lastly, number 46. Similar idea. You see that I use substitution again and again. So number 46. Limit x approaching 0 from positive side of tangent inverse of ln u. ln x, I mean. But when x going to 0 positive, what happened to the natural log of x? I wonder if you know this. This is negative infinity. Right? The graph of ln x looks like this. So as you go closer and closer to 0, the value of natural log will get closer to negative infinity. So this is limit natural log of x going to negative infinity of tangent inverse of ln x. We call that u. Limit u goes to negative infinity of tangent inverse u. We know this is negative infinity. I mean, sorry, negative pi over 2. Integral. Going back to the ones that you need to memorize, the derivative of sine inverse x respect to x is 1 over square root of 1 minus x squared. Now that implies the integral of 1 over square root of 1 minus x squared dx is sine inverse x plus constant. Okay, please memorize those three though. The derivative of sine inverse x, which is this one, derivative of tangent inverse x, the derivative of secant inverse x. You need to memorize the pattern. Now, once you memorize them, then you will recognize what to do when you do integration. Let me do number 60. I wonder if I did number 60 in my lecture. Number 60. Integral from 1/2 to 1 over radical 2 of 4 over square root of 1 minus x squared dx. But this is, you can move the 4 outside, right? One over square root of 1 minus x squared dx. Then this will be 4 times sine inverse x from 1/2 to 1 over radical 2, which is 4 times sine inverse of 1 over radical 2 minus sine inverse 1/2. Now you tell me, what is sine inverse 1 over radical 2? You know, if you don't memorize these special numbers, then you will have very hard time in this course. You need to memorize this. Okay? You need to memorize that. So sine inverse of 1 over radical 2 is pi over 4. Sine inverse of 1/2 is 30 degrees, pi over 6. Okay, so this is 4 times 3 pi minus 2 pi over 12. This is pi over 3. That's number 60. Number 62. Integral from 0 to radical 3 over 4 of dx over 1 plus 16x squared. Now, I will do substitution because this actually follows 1 over 1 plus 4x squared dx, right? Is it right? Let me rewrite it first then so that you can see better. So this is equals to integral from 0 to radical 3 over 4 dx over 1 plus 4x being squared. I will do substitution. So u equals to 4x, therefore du equals to 4dx. U radical 3 over 4 will be radical 3. U0 is 0. So now my integral becomes from 0 to radical 3, dx becomes du over 4 over 1 plus u squared. Now, in my opinion, from what I saw in the past, I have seen students kind of like rushing when they do the integrals. Instead of writing it properly, they try to finish the integration without rewriting the integration in a proper way. The key is actually rewriting your integration into a form that is easily recognized. So for example, once you are done that, the next thing I will write is this 1/4 integral from 0 to radical 3 of du over 1 plus u squared, right? The 1/4 outside is Mickey Mouse. The one inside is tangent inverse u from 0 to radical 3. But that's 1/4 tangent inverse of radical 3 minus tangent inverse of 0, which is 0. Okay, so this is 1/4 pi over 3, that's pi over 12. Okay. Now, side note. Notice that integral of dx over 1 plus x squared is equal to tangent inverse x plus constant, right? Now, I wonder if you remember what I did from the past on Wednesday. If I replace that x by mx, in this case 4x, what will that be? I wonder if you remember that. The linear transformation. So this will be equal to 1/4 tangent inverse for x plus constant. So if you happen to see that pattern, you can use this one. In other words, integral from 0 to radical 3 over 4 dx over 1 plus 4x being squared is 1/4 tangent inverse of 4x from 0 to radical 3 over 4. Oh, I would like to spend more time here instead of going further with number 64, 66, 68, and 70. Let me go over things that I think you need to memorize. Okay, to the point of you need to memorize. Okay, some important integrals from this section to memorize. The first one, the integral of 1 over square root of a squared minus x squared. The one we have is this integral of square root dx over 1 minus x squared. This one we know, this is sine inverse of x plus constant, right? Now, what happened if I replace that 1? What happened if I replace that 1 by a squared, something squared? And what will that be? Now, the key is to factor that square root of a squared out. And then later on, we do substitution. Let me show you. This is equal to integral dx square over square root of, I factor the a squared, 1 minus x squared over a squared. You see that? Which I will rewrite as, you know, on the denominator, square root of a squared becomes 1 over a integral dx over square root of 1 minus x over a quantity squared. But if you think about this, notice that x over a is the same to 1 over a times x, right? Okay, such that if you see that x over a, 1 over a here, you see this 1 over a here as the slope, as the coefficient of x, right? As the coefficient of x, then the integral of that must be the reciprocal of that slope times tangent inverse of x over, I'm sorry, not tangent inverse, sine inverse. Sine inverse of x over a plus constant, which will then give us a very nice result, sine inverse of x over a plus constant. Notice that I have done proofing here. I have done proofing here. So what is the integral of square root of a squared minus x squared? What is this equal to? It's equal to this. Okay, one way to prove this is you do the derivative of sine inverse that, and then you do chain rule here and there, and then you get 1 over square root of a squared minus x squared. Okay, so this is the first integral you need to memorize. Let me write it next door here. So the first integral that you need to memorize, because it shows up a lot. That's why I asked you to memorize that. Integral of dx over square root of a squared minus x squared equals to sine inverse of x over a plus constant. The second integral that shows up a lot, actually even more compared to the first one, is integral of 1 over a squared plus x squared. Now, it comes from the way we derive that has something to do with the tangent inverse one. So it's very similar to integral dx over 1 plus x squared, which is tangent inverse x. That's why you need to memorize that. Okay, what gives me what? So if I modify the constant becomes a squared, then I realize, you know what, let me factor that a squared. Which becomes 1 over a squared integral dx over 1 plus x over a squared. The same idea with what we did before. This is equal to 1 over a squared, the coefficient we already have at the front, times the reciprocal of the coefficient times tangent inverse of x over a, don't forget plus constant. So this will be 1 over a tangent inverse x over a plus constant. It shows up a lot. It shows up a lot such that I would like you to memorize this. Okay, memorize the work also though. I mean, you can go slower. Don't get me wrong. If you want to go slower, fine. You go slower here. Okay. If you want to go slower, then you say, oh, you know what? Let u equals to x over a. So my du is 1 over a dx, right? Then the substitution becomes 1 over a squared integral dx becomes a du over 1 plus u squared. A over a squared is 1 over a. Integral of du over 1 plus u squared is tangent inverse u plus constant, where my u, I substitute that back, is x over a. Okay, that's if you want to do it long way, which is not that long, not that long. But then it becomes substitution again. Okay, it trains your intuition when it comes to integration. What to substitute. Let me continue. We did number 62 earlier. How about number 64? I basically do the even number, which I think I already did in my lecture. Integral from 0 to sine x. I'm sorry. From 0 to pi over 2 of sine x over 1 plus cosine squared x dx. You see that if you use these cosine x as your u, if cosine x as your u, then you will end up with something over 1 plus u squared, right? And the derivative of cosine x is negative sine x. Oops, I'm sorry. So later on it becomes like, why does it want to be erased? It becomes like that, which is a lot easier to integrate. That will be negative tangent inverse of u, right? Now the thing is, you won't be able to see that instinct if you don't get used to do that, though. That's the thing. Okay, so let's do substitution. U equals to cosine x. So du will be negative sine x dx. Now then, u of pi over 2 is cosine pi over 2, that's 0. u0, that's cosine 0 is 1. So this integral now becomes integral from 1 to 0. Sine x dx is negative du over 1 plus u squared. I will reverse the order of integration and absorb the negative. This will be tangent inverse of u from 0 to 1. That's tangent inverse of 1 minus tangent inverse of 0. Tangent inverse of 1 is pi over 4. Tangent inverse of 0 is 0. Final answer, pi over 4. Number 66. Integral 1 over x square root of x squared minus 4 dx. We know that integral of 1 over x square root of x squared minus 1 dx, this is equals to secant inverse of x plus constant. Now the problem is we change that 1 becomes 4. Becomes 4. How to make it 1? I factor square root of 4 on from that square root. So I factor 4, then I get x squared over 4 minus 1, like that. Dx. Okay, now then square root of 4 comes out, becomes 1/2. Square root of x over 2 being squared minus 1 dx. From here, we do substitution. U equals to x over 2. So du is 1/2 dx. Oh, hold on. But that 1/2 dx is basically this guy together with this guy that will give me the du. Okay, okay, that's nice. I don't have to do it that way, but that's one way to do it. So this becomes integral. The yellow one becomes du. Okay, now how about x? X is 2u now, right? Square root of u squared minus 1. Now the thing is, the integral of this guy here, is what? That is secant inverse.
Mm-hmm.
Okay. Implicitly, we have done a problem, and the third integration that you would like to memorize, the third important integration that you would like to memorize. It doesn't show up that often. That's integral dx over x square root of x squared minus a squared equals to 1 over a secant inverse of x over a plus constant. That's the third important integration. Okay, now I will stop here for this 6.6. Let me go on to 6.8, at least the first couple sections. So 6.8, the first part. We will only do the basic L'Hopital rule. L'Hopital rule says the following. Let fx and gx are differentiable and g prime x is not equals to 0 on an open interval I containing A except at A. Okay, this is what the hypothesis is saying. Okay, so let's say this is the number line. Okay, and our interval I looks like this, an open interval I. Now, the function fx and gx has to be differentiable on this interval. Okay, and the derivative of gx is not equals to 0 except at one of the point there or some of the point there at A. So maybe 0 at A. Okay, but for sure that this both of them, fx and gx, has to be differentiable in this interval, and g prime x is not equals to 0 in this interval except at that A. Okay, now if we have this equation, and suppose two situations. The first one, both fx, I'm sorry, the limit. Both limit x going to infinity of fx equals to 0 limit x going to infinity of gx also equals to 0. Or the second case, limit x approaching a of fx is positive or negative infinity, limit x approaching a of gx is positive or negative infinity. So the first case, we will call that 0/0 case. The second case, we call that infinity over infinity case. Now, suppose we have either one of these cases, then actually this is not infinity, my bad. These are not infinity. Going to a. What am I doing? Then limit x approaching a of the quotient is equal to limit x approaching a of the quotient of the derivative. So you do the derivative on the top and the derivative at the bottom. Okay, so think of it this way. If you apply the limit on the numerator, that's infinity, the bottom also infinity or negative infinity, then you can apply this. Or if you apply a to the function on the top and the bottom, and then you get 0/0, then you can apply this. Now notice that L'Hopital rule is not the derivative of the ratio. This is not derivative of the ratio. No, it's derivative on the top divided by derivative at the bottom. So derivative over derivative. Okay, not derivative of the ratio, not derivative of the quotient, not quotient rule. You don't do quotient rule. Example. Let's see the problem. Number 8 first, which we can do using calculus 1 method. Number 8, limit x approaching 2 of x squared plus x minus 6 over x minus 2. Now, notice that if you plug 2 on the numerator, you will get 0. If you plug 2 on the denominator, you will get also 0. So this is 0/0 case. Now, according to L'Hopital rule, and every time I apply L'Hopital rule, I will put this notation here. Okay, do we have to do that, Thomas? No, you don't have to. I just do it myself so that when you read my notes, you know, oh, that's what Thomas did there. Thomas applied L'Hopital rule. Now, what will the L'Hopital rule be here? Well, the derivative of the numerator is 2x plus 1. The derivative of the denominator is just 1. Now I plug in numbers, right? That will be 2 times 2 plus 1 over 1. That's 5. Suddenly we have new method to compute the limit. While if we do it using calculus 1 method, if you use calculus 1 method, notice that you can factor the numerator. Becomes x plus 3, x minus 2 over x minus 2. And we can cancel x minus 2. The reason is x approaching 2, but x is not 2. Okay, x approaching 2 means x minus 2 approaching 0, but not equals to 0. In other words, we can cancel this. We can now cancel this, right? Because x minus 2 is not 0 anyway, so you can divide by x minus 2 on the top and at the bottom, and we end up with limit x approaching 2 of x plus 3, which is 2 plus 3, which is 5. Now, the thing is, this is factorable. The numerator is factorable, so we still can use calculus 1. What happened if this were, for example, what happened if this 6 were 7? Then suddenly it's not factorable, right? But we still can use L'Hopital rule. That's the strong point of this L'Hopital rule. It enables us to answer limit question without depending on the technique we have from calculus 1. Number 12. Limit x going to 0 of sine 4x over tangent 5x. When I plug in x equals to 0, I get sine 0, that's 0 on the top, and tangent 0, that's 0 at the bottom. So that's 0 over 0 case again. Therefore, I apply L'Hopital rule. This is equals to the limit x approaching 0 of 4 cosine 4x. The derivative of sine 4x is cosine 4x times 4. How about the derivative of tangent?
Cotangent?
No.
Oh no, it's one of those. That's right.
Memorize that. Somebody say something.
Right.
Secant squared. That's right.
That's right.
Derivative of tangent is secant squared. So this is secant squared of 5x times 5. Now then, when I plug in x equals to 0, I will get 4 cosine 0, which is 1, over 5 secant squared 0, which is still 1. Okay, cosine 0 is 1, secant 0 also equals to 1. Now the thing is, this actually also applies to infinity case. For example, number 20. Number 20, limit x goes to infinity of natural log of square root of x over x squared. If I plug in infinity to the top, I will get infinity. Plug it in infinity at the bottom, I also have infinity. So this is infinity over infinity case. Right? Let me modify it a little bit, the numerator. Natural log of square root is 1/2 natural log. Now then I apply L'Hopital rule, get limit x goes to infinity of 1/2 times 1 over x, right? The derivative of natural log is 1 over x. The derivative of x squared is 2x. Simplify, this is limit x goes to infinity of 1 over 4x squared, which is zero. Now, sometimes you need to do the derivative more than one time. Let's say number 24. I'll do it here. Number 24, limit u goes to infinity of u to the power, e to the power of u over 10 big over u cubed. This is infinity over infinity case. When I apply L'Hopital rules, limit u goes to infinity of e to the blah times the derivative of blah. Simplify a little bit. I get e to the u over 10 over 30 u squared. But still, when you apply infinity, you still get infinity over infinity. So I apply another L'Hopital rule. I hope you see that even though we don't get the answer right away, but after the same procedure 3 times, you will get the answer. Is e to the u over 10 times 1 over 10. At the bottom, you will get 60u. I'm sorry, it should be 1 over 10 here, not 1 over u. Which simplifies to be limit u goes to infinity of e to the u over 10 big over 600u. It's still infinity over infinity. When I plug in u equals to infinity, so apply another L'Hopital rule. So you see that I do L'Hopital rule 3 times. E to the u over 10 times 1 over 10 big over 600. This is limit u goes to infinity of e to the u over 10 over 6,000. Now the thing is, if you plug in infinity, on the top will be infinity, the bottom will be 6,000. So it is still infinity. Okay, now 0 over 0 or infinity over infinity, these two are called indeterminate form. Can be anything. We cannot tell. Can be anything. 0 over 0 may be, by the way, 0 over 0 may be 0. Maybe 0. Maybe 1. Or the same number divided, maybe 1. But somebody can also say this is equal to 2, by the way. Well, I mean, okay, let's look back. I hope you see the strange thing here. You can argue that 0 divided by anything is 0. Somebody else argue same number divided each other will be equals to 1. So at least you already have 2 solutions. That can be true, but at the same time, it violates the uniqueness of a solution. Like 0 over 0 equals to 0, at the same time equals to 1. Does it mean 0 equals to 1? Not supposed to, right? So even in that case, we already have indeterminate form. Not to say that somebody may say, oh, you know what? I don't like 0. I don't like 1. I like pi. Why? It's yummy. Okay. But why pi times? Well, because pi times 0 is 0, right? I mean, 6 divided by 2 equals to 3 because 3 times 2 equals to 6. So 0 over 0 equals to what? What times 0 equals to 0? Well, anything. Okay, anything. That's why that it becomes indeterminate form. Okay, that's why it becomes indeterminate form. Now, what the last example is doing is that it is possible you need to apply L'Hopital rule 3 times. Okay, that gives us some that gives us some hope though for guys. You know, if they try to date a girl and you get rejected twice, and you try again and again. Remember L'Hopital rules. Okay. The sad thing is it is possible that after you apply L'Hopital rule 3 times, you still get indeterminate form. And in this case, it's infinity. It's just like, okay, Thomas, you already asked me the same question 3 times. This is the 3rd time I reject you, and this is the last time I reject you. One more time, I will file for sexual harassment, for example, right? And then, of course, Thomas needs to stop. Even though it should not be called sexual harassment, though, all I ask is like, hey, you want to go out with me? Right? I don't, honestly, that kind of question, I don't see that as sexual harassment. But some people may interpret it that way, so be very careful, especially when you socialize. Okay, sometimes we are joking and other people don't see that as a joke. Let's just go out, man. I'm hungry. And that person see that as dating. Like if somebody asked me that question, Thomas, let's go out together. I will never think that person asked me to date. I will never have that. Why? I'm way too fugly. So under no circumstance somebody will ask me to go out. Okay, now in the later part of this section, we will see the variation of L'Hopital rules, but at least the first part of this section is doable with the basic L'Hopital rule. Okay, I think you can do this method from number 7 to number 33. Or maybe a bit more after that. Okay, I will stop here. And then on Wednesday, we will continue with the second part of 6.8. And then we move on with integration by parts 7.1. Okay, make sure you watch the lecture video. I don't think I have a time to go on with 7.2 on Wednesday, but let's take a look. So please watch the lecture video lesson 4. Okay. Basically the second part of week number 3. Okay, that's for today. See you then on Wednesday.